An EVPN fabric may advertise every tenant route correctly and still fail to carry a single useful packet. The reason is elementary. The outer VXLAN packet must first cross an ordinary IP network. That network is the underlay. Its task is not to understand tenants. Its task is to deliver packets between tunnel endpoints, predictably, at the required size, and through failures. The core learning is direct. Do not diagnose the overlay until every VTEP is provably reachable through the underlay. We shall build that proof from topology to packet capture. Here is our agenda. First, we shall establish why a leaf and spine fabric uses routed point-to-point links. Second, we shall separate stable loopback identities from the links that happen to carry them. Third, we shall choose a routing contract, install equal cost paths, and resolve an overlay next hop all the way to an egress interface. Fourth, we shall distinguish rapid failure detection from graceful state retention, then budget the tunnel overhead into the MTU. Finally, we shall define the positive and negative observations that prove one VTEP can deliver the required outer packet to every other VTEP. VXLAN places an original Ethernet frame inside UDP and an outer IP packet. The source and destination of that outer packet are VTEP addresses. The underlay forwards this outer packet exactly as it would any other IP traffic. It does not need the tenant's MAC address, subnet, VRF, or route target. That separation is a design invariant. Underlay routes describe infrastructure reachability. Overlay routes describe tenant services. Mixing those responsibilities makes failures harder to contain and evidence harder to interpret. Begin with one question. Can the underlay carry an outer packet from this VTEP address to that one? A folded cloth fabric gives every leaf a link to every spine. Traffic between two leaves therefore crosses one spine and has several paths of the same length. A leaf does not depend on another leaf as an accidental transit node. A spine does not become a tenant attachment point. This regularity is more important than the drawing's symmetry. It bounds the normal path, exposes missing adjacencies, and makes capacity growth repeatable. RFC 7938 describes this BGP-based data center design from operational experience. It is informative guidance, not an internet standard. The useful property here is the topology, independent of the chosen routing protocol. Between leaf and spine, use routed point-to-point links. This removes the shared Ethernet segment from the fabric's failure model. There is one neighbor at the far end, one routing adjacency, and one link whose loss can be withdrawn. Spanning tree is not selecting paths through the underlay. Routing is. Numbered links commonly use /31 or /30 prefixes. Some platforms and designs support IP unnumbered, often with IPv6 link local next hops. These are implementation choices, not different objectives. The objective is an explicit routed adjacency on every intended leaf-to-spine link, with no hidden Layer 2 transit dependency. A physical link address identifies an adjacency. A loopback identifies the device independently of any one link. Many designs use a router loopback for router, ID, and control sessions, and a VTEP loopback as the VXLAN source. They may be the same address in a small design, but their roles remain distinct. The critical property is stability. Losing one uplink must remove a path, not rename the tunnel endpoint. Advertise only the required infrastructure loopbacks into the underlay with explicit policy. Cisco and Arista examples source VXLAN from loopback interfaces. FR. Routing likewise requires the VTEP address to be reachable by remote VTEPs. The underlay may use an IGP such as OSPF or ISIS or external BGP on the fabric links. Reputable vendor designs support both. The wrong decision is not choosing one protocol over another. It is operating without a written contract. Define how loopbacks originate, how many equal paths are installed, what a leaf and a spine may advertise, and how sessions react to failure. With eBGP, define the autonomous system scheme and next hop behavior. With an IGP, define areas or levels and passive interfaces. Keep overlay address families and tenant policy out of this infrastructure contract. A flow diagram suggests several equal paths. It does not prove that the router installed them. Protocol selection, administrative distance, maximum path settings, next hop resolution, and hardware limits determine the forwarding entry. Inspect the route to a remote VTEP and count the resolved next hops. Then, inspect the forwarding, or ASIC, next hop group. Traffic is normally assigned by a flow hash, so equal cost does not imply equal packet counters at every instant. The proof is threefold. Every intended path is eligible, every next hop resolves through a live fabric link, and observed flows use more than one member without intolerable reordering. An EVPN route normally identifies a remote provider edge, or VTEP, as its BGP next hop. That address is useful only if the underlay resolves it. Follow the chain. The EVPN route points to a VTEP loopback. The underlay route to that loopback selects one or more fabric next hops. Each fabric next hop resolves to an adjacency and egress interface. The forwarding plane finally supplies the Layer 2 rewrite. A control plane route can therefore be present while its next hop is unusable. Do not stop at show BGP. Prove recursion until the final forwarding object is programmed. Bidirectional forwarding detection and BGP graceful restart solve different problems. BFD detects loss of a forwarding path quickly and can trigger withdrawal of the affected adjacency. Graceful restart allows a peer to retain routes while a control plane restarts on the assumption that forwarding state remains usable. One removes state after failure. The other deliberately preserves stale state during recovery. Combining them without an explicit model can create a longer black hole, not a safer network. State the timers, the failure being detected, whether forwarding survives, and the maximum interval during which stale reachability is acceptable. With an IPv4 outer header, VXLAN commonly adds 50 bytes to the inner IP packet, 20 bytes of outer IP, 8 of UDP, 8 of VXLAN, and 14 of inner Ethernet. Carrying a 1500-byte inner IP packet therefore requires an underlay IPMTU of at least 1550 in this simple case. An IPv6 outer header adds more. Tags, options, and platform accounting may change the interface value. Do not copy an MTU number without stating what it measures. Test the maximum intended payload with don't fragment semantics and confirm that packet too big feedback is neither blocked nor ignored. Addressing is not clerical work. It determines what can be filtered, summarized, recognized, and repaired. Give fabric links, router identities, and VTEP identities, explicit pools, and ownership rules. Use deterministic allocation so an engineer can infer the expected peer from the link or device position. Summarization can reduce state, but only where it preserves correct failure visibility. A surviving aggregate must not conceal that a particular VTEP has disappeared. IP unnumbered can reduce link address consumption, but it shifts the troubleshooting evidence toward interface identity and link local next hops. Whichever method is chosen, make uniqueness and role machine checkable. Before enabling or blaming EVPN, build a VTEP reachability matrix. From every local VTEP address, test every remote VTEP address. Verify the exact loopback route, not merely a covering default. Count the equal cost members in both routing and forwarding state. Send the largest required packet with the intended outer source and DF behavior. Remove one fabric link and observe the withdrawal interval, loss, and remaining paths. Capture at a boundary to confirm the expected outer source and destination. Add negative proof. No tenant prefix appears in the underlay, no unintended transit path is eligible, and no failed next hop remains programmed. A network is not resilient because its diagram contains two spines. Resilience is the observed result of specific failures. Remove one leaf-to-spine link, then remove an entire spine. Interrupt an underlay session while the link remains up. Withdraw one VTEP loopback. For each case, record detection time, packet loss, the next hop group before and after, and stability during recovery. Test partial failures, not only clean power-off events, a unidirectional path, an MTU mismatch, or a control plane that is alive while forwarding is not. The resulting matrix is the real design contract because it states what users experience. The core learning is this: the overlay inherits the underlay. Routed point-to-point links create a legible fabric. Stable loopbacks preserve endpoint identity as links change. A written routing contract originates only the required infrastructure reachability. Equal cost paths must exist in forwarding state, not merely on a diagram. Recursion must end at a programmed egress. Failure detection, graceful retention, and MTU each require their own test. Only then should an EVPN route be asked to carry service. Do not take the design on trust. Choose two VTEPs, follow the resolution chain, send the largest outer packet, remove one path, and observe the result.